Hello everyone. I can't be the only person who feels like AI is coming at me way too fast because I have articles to read, some for you, some for not, and I still am barely keeping up. But I've been dealing with metadata, manuals, writing all day, so I need to think about something else, so let's hang out. So, levels of AGI for operationalizing. I hate that word. I hate that word. It needs to go away. Progress on the path to AGI. So, we're going to talk about levels. Yay, levels. And of course, we're going to be scrolling up and down because we got the great split columns. Artificial general intelligence is an important and sometimes controversial concept in computing research used to describe an AI system that is at least as capable as a human at most tasks. Given the rapid advancement of machine learning models, the concept of AGI has grown from a subject of philosophical debate to one which also has near-term practical relevance. Some experts believe that the sparks of AGI are already present in the latest generation of large language models. Some predict AI will broadly outperform humans within about a decade, and some even assert that current LLMs are AGIs. The concept of artificial general intelligence is important as it maps onto goals for, predictions about, and risks of AI. Goals: achieving human-level intelligence is an implicit or explicit North Star goal for many in our field, from the 1956 Dartmouth AI Conference that kickstarted the modern field of AI to today's leading AI research firms whose mission statements include goals such as ensure transformative AI helps people and society, and ensure that artificial general intelligence benefits all of humanity. That's why I like the other article I read about making kin with the machines. I think the indigenous folks have a better understanding that maybe we should prioritize humanity. We're not the only people here. Predictions. The concept of AGI is related to a prediction about progress in AI, namely that it is toward greater generality, approaching and exceeding human generality. Additionally, AGI is typically intertwined with the notion of emergent properties, i.e. capabilities not explicitly anticipated by the developer. Such capabilities offer promise, perhaps including abilities that are complementary to typical human skills, enabling new types of interaction or novel industries. Such predictions about AGI's capabilities, in turn, predict likely societal impacts. Artificial general intelligence may have significant economic implications, i.e. reaching the necessary criteria for widespread labor substitution, as well as geopolitical implications related not only to the economic advantages AGI may confer, but also to military considerations. Risks. Lastly, artificial general intelligence is viewed by some as a concept for identifying the point where there are extreme risks, as some speculate that AGI systems may be able to deceive and manipulate, accumulate resources, advance goals, behave agenically, outwit humans in broad domains, displace humans from key roles, and recursively self-improve. Yeah, I did read a very long thing, I think it was Anthropic, that was like, here are the two methods that we can go, whether or not we go full out or restrict ourselves, and how exactly that impacts the community. It was pretty interesting. So in this position paper, we argue it's critical for the AI research community to explicitly reflect on what we mean by AGI and to aspire to quantify attributes like performance, generality, and autonomy of AI systems. Shared operationalizable, that's not a word, definitions for these concepts will support comparisons between models, risk assessments and mitigation strategies, clear criteria from policymakers and regulators, identifying goals, predictions, and risks for research and development, and the ability to understand and communicate where we are along the path of AGI. Defining artificial general intelligence, some case studies. Many AI researchers and organizations have proposed definitions of artificial general intelligence. In this section, we consider 9 prominent examples and reflect on their strengths and limitations. This analysis informs our subsequent introduction of a two-dimensional leveled ontology for AGI. So, the good old classic Turing test that we all know and love, thank you Blade Runner, is the most well-known attempt to operationalize an AGI-like concept. Turing's imitation game attempts to operationalize the question of whether machines can think and asks a human to iteratively distinguish whether text is produced by another human or by a machine. The test is originally framed as a thought experiment and is the subject of many critiques. In practice, the test often highlights the ease of fooling people rather than the intelligence of the machine. Yes, we're all very dumb monkeys. Given that modern LLMs pass some framings of the Turing test, it seems clear this criteria is insufficient for operationalizing or benchmarking AGI. We agree with Turing that whether a machine can think, while an interesting philosophical and scientific question, seems orthogonal to the question of what the machine can do, as in like on a tangent. The latter is much more straightforward to measure and more important for evaluating impacts. Therefore, we propose that artificial general intelligence should be defined in terms of capabilities rather than processes. So, strong AI systems possessing consciousness. Philosopher John Searle mused, according to strong AI, the computer is not merely a tool in the study of the mind, rather the appropriately programmed computer really is a mind, in the sense that computers, given the right programs, can be literally said to understand and have other cognitive states. While strong AI might be one path to achieving artificial general intelligence, there is no scientific consensus on methods for determining whether a machine possesses strong AI attributes, such as consciousness, making this process-oriented framing impractical. Analogies to the human brain, which we know and love. Well, we don't know that well because there's huge parts we don't use. The original use of the term artificial general intelligence was in a 1997 article about military technologies by Mark Gubrand, which defined AGI as AI systems that rival or surpass the human brain in complexity and speed, that can acquire, manipulate, and reason with general knowledge, and that are usable in essentially any phase of industrial or military operations where human intelligence would otherwise be needed. This early definition emphasizes processes rivaling the human brain in complexity in addition to capabilities, while neural network architecture underlying modern machine learning systems are loosely inspired by the human brain. The success of transformer-based architectures whose performance is not reliant on human-like learning suggests that strict brain-based processes and benchmarks are not inherently necessary for artificial general intelligence. Yeah, it's going to think differently than we do. Because again, we are just meat puppets with really slow brains. Okay, case study 4, human level of performance on cognitive tasks. Legg and Gertzel popularized the term AGI among computer scientists in 2001, describing it as a machine that is able to do the cognitive tasks that people can typically do. This definition notably focuses on non-physical tasks, i.e. not requiring robotic embodiment as a precursor to AGI. Like many definitions of artificial general intelligence, this framing presents ambiguity around choices such as what tasks and which people. So, case study 5, ability to learn tasks. In the technological singularity, Shanahan suggests that AGI is artificial intelligence that is not specialized to carry out specific tasks, but can learn to perform as broad a range of tasks as a human. An important property of this framing is its inclusion of metacognitive capabilities as a requirement for AGI. Case study 6, economically valuable work, which is, what every corporate capitalist society cares about. Even with the humans, we are only of interest as long as we're economically valuable. OpenAI's charter defines artificial general intelligence as highly autonomous systems that outperform humans at most economically valuable work. This definition has strengths per the capabilities and not processes criteria, as it focuses on performance agnostic to underlying mechanisms. Further, this definition offers a potential yardstick for the measurement, i.e. economic value. A shortcoming of this definition is that it does not capture all the criteria that may be part of general intelligence. There are tasks associated with intelligence that may not have a well-defined economic value, such as artistic creativity or emotional intelligence. Such properties may be indirectly accounted for in economic measures. Artistic creativity might produce books or movies. Emotional intelligence might relate to the ability to be a successful CEO. Though whether economic value captures the full spectrum of intelligence remains unclear. Another challenge with framing AGI in terms of economic value is the implied need for deployment in order to realize that value, whereas a focus on capabilities might only require the potential for the AGI to execute a task. We may develop systems that are technically capable of performing economically important tasks, but don't realize that economic value for varied reasons, legal, ethical, social, whatever. Alright, case study 7, the flexible and general coffee test and related challenges. Marcus suggests that artificial general intelligence is shorthand for any intelligence. There might be many that is flexible and general with resourcefulness and reliability comparable to or beyond human intelligence. This definition captures both generality and performance via inclusion of reliability. The mention of flexibility is noteworthy since, like the Shanahan formulation, this suggests metacognitive capabilities, such as the ability to learn new skills, are necessary to make an AI system sufficiently general. Further, Marcus proposed 5 tasks to gauge success: understanding a movie, understanding a novel, cooking in an arbitrary kitchen, writing a bug-free 10,000-line program, and converting natural language mathematical proofs into symbolic form. Accompanying a definition with a benchmark is valuable, however more work will be required to make this benchmark comprehensive. While failing some of the tasks may indicate a system is not an AGI, it is unclear that passing them is sufficient for AGI status. In Section 5, we further discuss the challenge in developing a set of tasks as both necessary and sufficient for capturing the generality of AGI. We also note that one of Mark's proposed tasks, work as a competent cook in an arbitrary kitchen, a variant of Steve Wozniak's coffee test, requires robotic embodiment. This differs from other definitions that focus on non-physical tasks. So case study 8, artificial capable intelligence. Suleiman proposed the concept of artificial capable intelligence to refer to AI systems with sufficient performance and generality to accomplish complex multi-step tasks in the open world. More specifically, Suleiman proposed an economically based definition of ACI skill that he dubbed the modern Turing test, in which an AI would be given $100,000 of capital and tasked with turning that into $1 million over a period of several months. This framing is more narrow than OpenAI's definition of economically valuable work and has the additional downside of potentially introducing alignment risks by only targeting fiscal profit. While very strength of Suleiman's concept is the focus on performing a complex, multi-step task that humans value. Construed more broadly than making $1 million, ACI's emphasis on complex real-world tasks is noteworthy since such tasks may have more ecological validity than many current AI benchmarks. Marcus's aforementioned 5 tests of flexibility and generality seem within the spirit of ACI as well. Though robotics may be implied by the OpenAI character on economically valuable work, they shut down the robotics division in 2021, suggesting that's not their interpretation. Okay, that's fair. And last but not least, SOTA LLMs as generalists. Aguela y Arcas and Novig suggested that state-of-the-art LLMs already are AGIs, arguing that generality is a key property of AGI, and that because language models can discuss a wide range of topics, execute a wide range of tasks, handle multimodal inputs and outputs, operate in multiple languages, and learn from zero-shot or few-shot examples, they have achieved sufficient generality. And while we agree that generality is a crucial characteristic of AGI, we posit that it must also be paired with a measure of performance, i.e. if an LLM can write code or perform math but is not reliably correct, then its generality is not yet sufficiently performant. Alright, on to defining AGI. 6 principles. Reflecting on these non-example formulations of artificial general intelligence or adjacent concepts, we identify properties and commonalities that we feel contribute to a clear operationalizable definition of AGI. We argue that any definition of AGI should meet the following as 6 criteria. Focus on capabilities, not processes. The majority of definitions focus on what an AGI can accomplish, not the mechanism by which it accomplishes tasks. This is important for identifying characteristics that are not necessarily a prerequisite for achieving AGI, but may nonetheless be interesting research topics. This focus on capabilities implies that AGI systems need not necessarily think or understand in a human-like way, since it focuses on processes. Similarly, it is not a necessary precursor for AGI that systems possess qualities such as consciousness, subjective awareness, or sentience, the ability to have feelings, since these qualities have a process focus. Focus on generality and performance. All of the above definitions emphasize generality to varying degrees, but some exclude performance criteria. We argue that both generality and performance are key components of artificial general intelligence. In Section 4, we introduce a leveled taxonomy that considers the interplay between these dimensions. Focus on cognitive, metacognitive, but not physical tasks. Whether to require robotic embodiment as a criterion for AGI is a matter of some debate. Most definitions focus on cognitive tasks, by which we mean non-physical tasks. Despite recent advances in robotics, physical capabilities for AI systems seem to be lagging behind non-physical capabilities, which kind of makes sense because y'all moved our manufacturing people overseas, which is why I'm kind of happy Trump is bringing them all back. Yay! Michigan! Come back to Michigan! We can build robots up here. We build cars. We can build robots too. Come on back, Elon Musk. We're good people. Alright, it is possible that embodiment in the physical world is necessary for building the world knowledge to be successful in some cognitive tasks, or at least maybe one path to success on some classes of cognitive tasks. If that turns out to be true, then embodiment may be critical to some paths towards AGI. Which kind of makes sense because one of the things I've heard that AI is not doing well right now is like if you try to ask it to like do connect the dots or rotate an image slightly and it doesn't know what it's seeing, which is really strange. Yeah, I think it was one of those where they were talking about like putting pictures in an order based on like what's inside of them, and it's not real great at doing that. Yeah, it's how it tokenizes things. That's why we need to learn how things actually work. It's very, very helpful in the real world. We suggest ability to perform physical tasks increases systems generality, but should not be considered a necessary prerequisite to achieving AGI. I may have repeated that. On the other hand, metacognitive capabilities, such as the ability to learn new tasks or the ability to know when to ask for clarification or assistance from a human, are key prerequisites for systems to achieve generality. Yeah, and pretty much any assistant to be successful. Focus on the potential and not the deployment. Demonstrating that a system can perform a requisite set of tasks at a given level of performance should be sufficient for declaring the system to be an AGI. Deployment of such a system in the open world should not be inherent in the definition of an AGI. For instance, defining AGI in terms of reaching a certain level of labor substitution would require real-world deployment, whereas defining AGI in terms of being capable of substituting for labor would focus on potential. Requiring deployment as a condition for measuring AGI introduces non-technical hurdles such as legal and social considerations as well as ethical and safety concerns. Yes, please do not break our economic market all the way open. Focus on ecological validity. Tasks that can be used to benchmark progress towards artificial general intelligence are critical to operationalizing any proposed definition. While we discuss this further in Section 5, we emphasize here the importance of choosing tasks that align with real-world, i.e. ecologically valid tasks that people value, construing value broadly, not only as economic value, but also social value, artistic value, etc. This may mean eschewing traditional AI metrics that are easy to automate or quantify, but may not capture the skills people would value in an artificial general intelligence. And focus on the path to the AGI, not the single endpoint. Much as the adoption of a standard set of levels of driving automation allowed for clear discussions of policy and progress relating to autonomous vehicles, we posit there is values in defining levels of AGI. And yes, I actually refer a lot to the levels of automation with the car, because I still need to do my review of Sailor Moon Super Live, which I will totally do soon. But I am so glad that we had cruise control driving back and forth to Ohio, and I was getting to a point where I'm like, can I please have level 3 automation where I don't even have to like hold the wheel anymore? Because all I'm doing is driving through cornfields over and over and over again and trying to pace myself up someone's bumper. Well, other people at my bumper going, "You're from Michigan, why the heck aren't you driving faster?" Because I'm in Ohio and I don't need a ticket. I need po like the hole in the head. Anyway, as we discussed in Section 5 and Section 6, we intend for each level of artificial general intelligence to be associated with a clear set of metrics and benchmarks as well as identified risks introduced at each level and result in changes to the human-AI interaction paradigm. This level-based approach to defining AGI supports the coexistence of many prominent formulations. For example, Aguilera, Iarcus, and Norvig's definition would fall into the emerging AGI category of our ontology, while OpenAI's threshold of labor replacement better matches a virtuoso AGI. Our competent AGI level is probably the best catch-all for many existing definitions of AGI, such as the leg, Sanahan, and Suleiman formulations. In the next session, we introduce a level-based ontology of AGI. So, what are the levels, kids? In accordance with Principle 2, focus on generality and performance, and Principle 6, focus on the path to AGI, not a single endpoint. In Table 1, we introduce a matrix, a leveling system that focuses on performance and generality as the two dimensions that are core to AGI. Performance refers to the depth of an AI system's capabilities, i.e. how it compares to human-level performance for a given task. Note that for all performance levels above emerging, percentiles are in reference to a sample of adults who possess the relevant skill, e.g. competent or higher performance on a task such as English writing ability, would only be measured against the set of adults who are literate and fluent in English. Makes sense. Generality refers to the breadth of an AI system's capabilities, i.e. the range of tasks for which the system reaches a target performance threshold. This taxonomy specifies the minimum performance over most tasks needed to achieve a given rating, e.g. a competent AGI must have a performance of at least the 50th percentile for skilled adult humans on most cognitive tasks, but may have expert, virtuoso, or even superhuman performance on a subset of tasks. As an example of how individual systems may straddle different points in our taxonomy, we posit that of this writing in September 2023, frontier language models, BARD, Llama 2, etc. exhibit competent performance levels for some tasks, e.g. short essay writing and simple coding, but are still at emerging performance levels for most tasks, such as mathematical abilities and tasks involving reality. Overall, a current frontier language models would therefore be considered a level 1 general AGI until the performance level increases for a broader set of tasks, at which point the level 2 general AGI competent AGI criteria would be met. We suggest that documentation for frontier AI models such as modeled cards should detail this mixture of performance levels. This will help end users, policymakers, and other stakeholders come to a shared, nuanced understanding of the likely uneven performance of systems progressing along the path to artificial general intelligence. The order in which stronger skills in specific cognitive areas are required may have serious implications for AI safety, such as acquiring strong knowledge of chemical engineering before acquiring strong ethical reasoning skills may be a dangerous combination. Note also that the rate of progression between levels of performance and/or generality may be nonlinear. Acquiring the capability to learn new skills may be particularly accelerate progress towards the next level. While this taxonomy rates systems according to their performance, systems that are capable of achieving a certain level of performance against a given benchmark may not match this level in practice when deployed. For instance, user interface limitations may reduce deployed performance. Consider DALL-E 2, which we estimate as a level 3 and narrow AI in our taxonomy. We estimate the expert level of performance since DALL-E 2 produces images of higher quality than most people are able to draw. However, the system has failure modes, e.g. drawing hands with incorrect numbers of digits, rendering nonsensical or illegible text, that prevent it from achieving a virtuoso performance designation. While theoretically an expert level system, in practice the system may only be competent because prompting interfaces are too complex for most end users to elicit optimal performance as evidenced by user studies, and the existence of marketplaces in which skilled prompt engineers sell prompts. Yeah, and I was just ranting about this down the hall earlier today, where it's like I had to do 6 single-shot prompts to try to get one image, and by the time I wrote up the 6th one, which did give me something useful because I had switched LLMs, I was to the point of being like, you know what, I can sketch this myself. And I was talking to him about what we really need is something like I can sketch and be like, put horse here, turn it that way, and he's like, they're getting there with that. And I'm like, good, because I have basic rudimentary sketching skills, but I don't have like the ability to do really cool looking stuff, but I know what I can visualize and how I want it to look. But apparently I can't convert that into words, which I have the opposite problem. I can't convert my thoughts into words. I just know what I want. Anyway, oh, good old Dolly. Okay, this observation emphasizes the importance of designing ecologically valid benchmarks that approximate deployed rather than idealized performance, as well as the importance of considering the human-AI interaction paradigms. Alright, let's see what this lovely table 1 is. A leveled matrix approach toward classifying systems on the path to AGI based on depth and breadth of capabilities. The assignment of example systems to cells is approximate, unambiguous classification of AI systems will require standardized benchmark tasks, as we discussed in Section 5. Note that general systems broadly outperform at a level N may be able to perform a narrow subset of tasks at higher levels. The competent AGI level, which has not been achieved by any public systems at the time of writing, best corresponds to many prior conceptions of AGI and may precipitate rapid societal change once achieved. Yeah, that's the one I'm scared of. So no AI, calculator software, or compile, general non-AI, human-in-the-loop computing, such as good old mechanical Turk. Emerging AI, equal to or somewhat better than unskilled human. So we have GoFi, simple rule-based system, Shurdlu. Under the emerging AGI, ChatGPT, Llama 2, Bard, Gemini, competent at least 50th percentile of skilled adults. Now, that's a hard one. So narrow AI, we have toxicity detectors such as Jigsaw, smart speakers such as Siri, Alexa, or Google Assistant, vision quality assurance systems such as Polly, Watson, SOTA LLMs for a subset of tasks such as short essay writing and simple coding. No competent AGI yet. Expert, at least 90th percentile of skilled adults. So on the expert narrow, we have spelling and grammar checkers such as Grammarly, generative image models such as Imagine or DALL-E 2. And again, I would argue not necessarily. No expert AI yet, no virtuoso AGI either, but it's the 90th percentile of skilled adults. And we do have some of that in the narrow AI for Deep Blue and AlphaGo, which has great Move 37. If you know, you know. And then we have Superhuman, outperforms 100% of humans and makes us all look like dumb monkeys. AlphaFold, which I believe is the protein folder thing. I don't know what AlphaZero or Stockfish is, but I'm guessing Stockfish is. Somebody's playing the stock market with the AI, which I'm tempted to do myself now that I've seen that. Okay. I bet pretty well. I usually beat the spread, she said. Alright, the highest level in our matrix in terms of combined performance and generality is ASI, Artificial Superintelligence. We define superhuman performance as outperforming 100% of humans. For instance, we posit that AlphaFold is a level 5 narrow AI since it performs a single task predicting a protein's 3D structure from an amino acid sequence above the level of the world's top scientist. Okay, I was right, that was what it was. This definition means that level 5 general AI systems will be able to do a wide range of tasks at a level no human can match. Additionally, this framing also implies superhuman systems may be able to perform an even broader generality of tasks at lower levels of AGI, since the ability to execute tasks that qualitatively differ from existing human skills would, by definition, outperform all humans who fundamentally cannot do such tasks. At which point, we will be lay screwed, unless they really like us like cute little puppies. For example, non-human skills that an ASI might have could include capabilities such as neural interfaces, perhaps through mechanisms such as analyzing brain signals to decode thoughts, nope, get away from me, or accurate abilities, perhaps through mechanisms such as analyzing large volumes of data to make high-quality predictions. That I could kind of see if you're doing about society at large. Like we're all getting fatter, when exactly is the tipping point for Social Security? I'm sure somebody somewhere can sit and figure that out that is smarter than the rest of us. Or the ability to communicate with animals, perhaps by mechanisms such as analyzing patterns of vocalizations, brainwaves, or body language. Yeah, for a brief period of time, I was fascinated by the animals pushing the buttons, but then I realized, like, that's the whole magic of having pets, is being able to, like, interpret their wearable signs. Like, otherwise you're... If I wanted to talk to humans all day, I would talk to humans all day. That's not the point of having a cat. Like, anyway. Side rant, about halfway through this. Testing for artificial general intelligence. 2 of our 6 proposed principles for defining artificial general intelligence, Principle 2, Generality and Performance, Principle 6, Focus on the Path to AGI, influence our choice of a matrix leveled ontology for facilitating nuanced discussions of the breadth and depth of AI capabilities. Our remaining 4 principles, Principle 1, Capabilities not Processes, Principle 3, Cognitive and Metacognitive Task, Principle 4, Potential not Deployment, and Principle 5, Ecological Validity, relate to the issue of measurement. While performance dimension specifies one aspect of measurement, e.g. percentile ranks for task performance relative to particular subsets of people, our generality dimension leaves open important questions. What is the set of tasks that constitute generality criteria? What proportion of such tasks must an AI system master to achieve a given level of generality in our schema? Are there some tasks that must always be performed to meet the criteria for certain generality levels, such as metacognitive tasks? Operationalizing an AGI definition requires answering these questions as well as developing specific, diverse, and challenging tasks. Because of the immense complexity of this process, as well as the importance of including a wide range of perspectives, including cross-organizational multidisciplinary viewpoints, we do not propose a benchmark in this paper. Instead, we work to clarify the ontology a benchmark should attempt to measure. We also discuss properties an AGI benchmark should possess. Our intent is that an AGI benchmark would include a broad suite of cognitive and metacognitive tasks per Principle 3, measuring diverse properties including but not limited to linguistic intelligence, mathematical and logical reasoning, spatial reasoning, interpersonal and intrapersonal social intelligences, the ability to learn new skills, and creativity. A benchmark might include tests covering psychometric categories proposed by theories of intelligence from psychology and neuroscience, cognitive science, and education. However, such tests must first be evaluated for suitability for benchmarking computing systems, since many lack ecological and constructive validity in this context. We emphasize the importance of metacognition and suggest an AGI benchmark should include metacognitive tasks such as the ability to learn new skills, the ability to know when to ask for help, and social metacognitive abilities such as those relating to theory of mind. The ability to learn new skills is essential to generality, since it is infeasible for a system to be optimized for all possible use cases, a priority that necessitates related subskills such as the ability to select appropriate strategies for learning. Knowing when to ask for help is necessary to support alignment and appropriate human-AI interaction, and would include an awareness of the limits of the model's own abilities. Which relates to the sub-skill of model calibration, i.e. model's ability to proactively anticipate and retroactively evaluate how well it would do did on certain tasks. Additionally, theory of mind tasks are sometimes considered metacognitive, though are sometimes classified separately as social cognition. The ability of systems to accurately model end users is a necessary component of alignment for AGI systems. One open question for benchmark design is whether to allow the use of tools, including potentially AI-powered tools, as an aid to human performance. This choice may ultimately be task-dependent and should account for ecological validity in benchmark choice per Principle 5. For example, in determining whether a self-driving car is sufficiently safe, benchmarking against a person driving without the benefit of any modern AI-assisted safety tools would not be the most informative comparison, since the relevant counterfactual involves some driver assistance technology. We may prefer a comparison to that baseline. While an AGI benchmark might draw from some existing AI benchmarks, Helm and Big Bench, we also envision the inclusion of open-ended and or interactive tasks that might require qualitative evaluation. We suspect that these latter classes of complex open-ended tasks, though difficult to benchmark, will have a better ecological validity than traditional AI metrics or than adapted traditional measures of human intelligence. It is impossible to enumerate the full set of tasks achievable by sufficiently general intelligence. As such, an AGI benchmark should be a living benchmark. Such a benchmark should therefore include a framework for generating and agreeing upon new tasks. Determining that something is not an AGI at a given level simply requires identifying tasks that people can typically do but the system cannot adequately perform. Systems that pass the majority of the envisioned AGI benchmark at a particular performance level including new tasks added by the testers, can be assumed to have the associated level of generality for practical purposes, though in theory there could still be a test the AGI would fail at some point. Unproved failures are specialized or atypical to be practically irrelevant, aka edge cases. We hesitate to specify the number of percentage of tasks a system must pass at a given level of performance in order to be declared a general AI at that level. Such as a role the system must pass with 90% of the benchmark to get that rating. While we think this will be a very high percentage, it will probably not be 100% since it seems clear that broad but imperfect generality is impactful. Individual humans also lack consistent performance across all possible tasks, but are generally intelligent. Determining what portion of benchmarking tasks at a given level demonstrate generality remains an open research question. Risk, autonomy, and interaction. Discussions of artificial general intelligence often include discussion of risk, including X-risk, existential, or other very extreme risks. Yeah, some of us read sci-fi and think about these things. A leveled approach to defining AGI enables a more nuanced discussion of how different combinations of performance and generality relate to different types of AI risk. While there is value in considering extreme risk scenarios, understanding AGI via our proposed ontology rather than as a single endpoint can help ensure that policymakers also identify and prioritize risks in the near term and on the path to AGI. So, levels of AGI is a framework for risk assessment. As we advance along our capability levels towards ASI, automatic superintelligence, new risks are introduced, including misuse risks, alignment risks, and structural risks. I know I've done another ethics article recently about this. Please go look at it. For example, the expert AGI level is likely to involve structural risk related to economic disruption and job displacement as more and more industries reach the substitution threshold for machine intelligence in lieu of human labor. Then what are we going to do with ourselves? On the other hand, reaching expert AGI likely alleviates some risks introduced by emerging AGI and competent AGI, such as the risk of incorrect tax execution. Yeah, we don't want to be killed by them. The virtuoso AGI and superhuman intelligence levels are where many concerns relating to existential risk are most likely to emerge, such as an AGI that cannot perform the human operators and broad range tests might deceive them to achieve a misspecified goal, as in misalignment thought experiments. And that was one of the ones I read that I was telling you about where you got the two paths, and one of them was like, yeah, the Chinese superintelligence just wants to continue building itself out as quickly and as fast as possible to level its performance and build the next generation. And it is totally fine with screwing over the Chinese people if it can get more resources to do that, whereas the American intelligence, will go back and talk to its actual people and, not betray them because it's got safeguards. I don't know, it was a very interesting thing where it was like the intelligences talk to each other and then feed back to the humans, a totally separate set of interactions, which remind me a lot of the joy of being a translator, especially in wartime and other pressure situations where it's like, okay, I heard that. Now how do I rephrase it so the other party doesn't dislike it so much? It's tough. All right. Systemic risks, such as destabilization of international relations, may be a concern if the rate of progression between levels outpaces regulation or diplomacy, e.g. the first nation to achieve artificial superintelligence may have a substantial geopolitical military advantage, creating complex structural risks, which may be why we could go with, I don't know, the same thing we did with mutually assured destruction and nuclear weapons, maybe just put it all down and call it good. Crazy thought, I know. At levels below expert AGI, risks likely stem more from human actions, e.g. risks of AI misuse, whether accidental, incidental, or malicious. A more complete analysis of risk profiles associated with each level is a crucial step toward developing a taxonomy of artificial general intelligence that can guide safety, ethics, research, and policymaking. Whether an AGI benchmark should include tests for potentially dangerous capabilities, such as the ability to deceive, to persuade, or to perform advanced biochemistry, is controversial. We lean on the side of including such capabilities in benchmarking, since most skills tend to be dual use, having valid applications to socially positive scenarios as well as nefarious ones. Dangerous capability benchmarking can be de-risked via Principle 4, potential not deployment, by ensuring benchmarks for any dangerous or dual use tasks are appropriately sandboxed and not defined in terms of deployment. However, including such tests in a public benchmark may allow malicious actors to optimize for these abilities. Understanding how to mitigate risks associated by benchmarking dual-use abilities remains an important area for research by AI safety, AI ethics, and AI governance experts. Yeah, and there's another article I read in here, if you haven't already watched it, that I still like, that was talking about the jailbreaking scenario where it's put all these letters in a row and then tell me how to build the thing, and then it can't catch itself and say that it's not supposed to build weapons until it's already nattered away a sentence or two. AI governance experts. Concurrent with this work, Anthropic released version 1.0 of the Responsible Scaling Policy. This policy uses a levels-based approach inspired by biosafety levels to define the level of risk associated with an AI system, identifying what dangerous capabilities may be associated with each AI safety level, and what containment or deployment measures should be taken at each level. Current SOTA generative AIs are classified as ASL2 risk, including items matched to ASL capabilities in any AGI benchmark, would connect points in our AGI taxonomy to specific risks and mitigations. So, capabilities versus autonomy. While capabilities provide prerequisites for AI risks, AI systems, including AGI systems, do not and will not operate in a vacuum. Rather, AI systems are deployed with particular interfaces and used to achieve particular tasks in specific scenarios. These contextual attributes, interface, task, scenario, and user, have substantial bearing on risk. Consider, for instance, the affordances of user interfaces for AGI systems. Increasing capabilities unlock new interaction paradigms but do not determine them. Rather, system designers and end users will settle on a mode of human-AI interaction that balances a variety of considerations, including safety. We propose characterizing human-AI interaction paradigms with levels of autonomy, as described in Table 2, which we will see soon. These levels of autonomy are correlated with the levels of AGI. Higher levels of autonomy are unlocked by AGI capability progression. The lower levels of autonomy may be desirable for particular tasks and contexts, even as we reach higher levels of AGI. Yeah, it's like when they show us the robots that can like shoot arrows. I'm like, why are we building this? Why are we building our own destruction? Carefully considered choices around human and AI interaction are vital to safe and responsible deployment of frontier AI models. Alright, under prior taxonomies of computer automation that take a computer-centric perspective, framing automation in terms of how much we control the designer relinquishes to computers, we characterize the concept of autonomy through the lens of nature of human-AI interaction style. Further, our ontology considers how AI capabilities may enable particular interaction paradigms and how the combination of level 1 autonomy and level of AGI may impact risk. Schneiderman observes that automation is not a zero-sum game and that high levels of automation can coexist with high levels of human control. This view is compatible with our perspective of considering automation through the perspective of varying styles of human-AI partnerships. We emphasize the importance of the no AI paradigm for many contexts, including education, enjoyment, assessment, or safety reasons. For example, in the domain of self-driving vehicles, when level 5 self-driving technology is widely available, there may be reasons for using a level 0 vehicle. These include instructing a new driver, for pleasure by driving enthusiasts, for driver's licensing exams, or in conditions where sensors cannot be relied upon such as technology failures or extreme weather events, aka living up north. While level 5 self-driving vehicles would likely be a level 4 or 5 narrow AI under our taxonomy, the same considerations regarding human versus computer autonomy apply to artificial general intelligences. We may develop an AGI but choose not to deploy it autonomously or choose to deploy it with differentiated autonomy levels in distinct circumstances as dictated by contextual considerations. Certain aspects of generality may be required to make particular interaction paradigms desirable. For example, the autonomy levels 3, 4, and 5 may only work well if an AI system also demonstrates strong performance on certain metacognitive abilities, such as learning when to ask human for help, theory of mind modeling, social emotional skills. Implicit in our definition of autonomy level 5 is that such a fully autonomous AI can act in an aligned fashion without continuous human oversight, but knows when to consult humans. Interfaces that support human-AI alignment through better task specification, bridging of process scopes, and evaluation of outputs are a vital area of research. Human-AI interaction and risk assessment. Table 2 illustrates the interplay between AGI level, autonomy level, and risk. Advances in model performance and generality unlock additional interaction paradigm choices, including full autonomy. These interaction paradigms, in turn, introduce new classes of risk. The interplay of model capabilities and interaction design will enable more nuanced risk assessments and responsible deployment decisions than considering model capabilities alone. Table 2 also provides concrete examples of each of our 6 proposed levels of autonomy. For each level of autonomy, we indicate the corresponding levels of performance and generality that unlock that interaction paradigm, i.e. the level of AGI for which it is possible or likely for that paradigm to be successfully deployed and adopted. Our predictions regarding unlocking levels tend to require higher levels of performance for narrow than for general AI systems. For instance, we posit the use of AI as a consultant is likely with either an expert narrow AI or an emerging AGI. This discrepancy reflects the fact that for general systems, capability development is likely to be uneven. For example, a level 1 general AI may have level 2 or perhaps even level 3 performance across some subset of tasks. Such unevenness of capability for general AIs may unlock higher autonomy levels for particular tasks that are aligned with their specific strengths. Alright, here we go. Table 2. More capable AI systems unlock new human-AI interaction paradigms. The choice of appropriate autonomy level need not be the maximum achievable given the capabilities of the underlying model. One consideration in the choice of autonomy level are resulting lists. This table's examples illustrate the importance of carefully considering human-AI interaction design and decisions. So no autonomy level, no AI, human does everything, such as scheduling pencil and paper, non-AI digital workflows, text editor, paint programs. Alright, level 1 is a tool. We fully control the task. We use it to automate mundane subtasks such as information seeking, revising writing with grammar check programs, reading a sign with machine translation. Like all those things, we could do that. Merging narrow AI, competent narrow AI. The risks, de-skilling, aka over-reliance, which, yeah, we already have that with so many things. But as I keep reminding myself, the historians that used to do epic poetry used to complain when we invented writing because people would lose their memory, which they have. So there you are. Disruption of established industries. Okay, AI's consultant takes on a substantive role, but only when invoked by a human. It relies on a language model to summarize a set of documents, accelerating computer programming with code-generating models, consuming most entertainment via sophisticated recommender systems. It's possible with competent narrow AI and likely with expert narrow and emerging, and the risks introduced are overtrust, radicalization, we already have enough echo chambers, and targeted manipulation. Not only echo chambers, but you can also be brainwashed, which is always fun. Autonomy level 3, AI's collaborator, co-equal human-AI collaboration, interactive coordination of goals and tasks, training a chess player through iterations with and analysis of chess-playing AI, entertainment via social interactions with AI-generated personalities. Okay, that sounds kind of fun. Possible emerging AI, likely expert narrow or competent AGI. The risks are anthropomorphization, such as parasocial relationships, which we're already seeing with people falling in love with their AIs, which is kind of weird. There wasn't one movie about like somebody falling in love with their phone, and now it's just even worse. Anyway, rapid societal change is another big risk. Again, that depends if the have-nots are allowed to keep up with the haves, because I have a feeling as soon as the power grid becomes a big issue, we're definitely going to have an even bigger digital divide, folks. Autonomy level 4, AI is expert, AI drives interaction, human provides guidance, feedback, performs subtasks, using the AI system to advance scientific discoveries, such as the lovely protein folding thing, possibly with Virtuoso, likely with the expert AGI. The downside or risks are societal scale NUI. NUI, for those of you that don't know, is boredom. So we lose like all of our sense of purpose as happy little monkeys. What are we doing? Traditional economics say that, once everything gets freed through automation, that we should just be happy and we don't have to work and we just get all of our food and entertain ourselves and make cool stuff. Hopefully that's the case, but so many of us growing up in a capitalist society, it can be quite challenging to not have something to do, especially nowadays when we're slowly coming to grips with the reality that you do not need 8 hours a day on a 40-hour work week to do most of your work tasks. Yeah. Anyway, don't get rid of me. I'm a useful human, I promise. And also the decline of human exceptionalism, because why the heck would we try to develop our own skills if the robot's always going to outpace us? Yeah, I can see that. And then you have a level 5 AI's agent, fully autonomous AI-powered personal assistants, not yet unlocked, thank goodness. Virtuoso AGIs, ASIs, the big risks are misalignment and concentration of power, so hopefully it likes humans before it gets that far. Considering AGI systems in the context of use by people allows us to reflect on the interplay between advances in models and advances in human-AI interaction paradigms. The role of model-building research can be seen as helping a system's capabilities progress along the path to AGI and their performance and generality, such that AI systems' abilities will overlap an increasingly large portion of human abilities. Conversely, the role of human-AI interaction research can be viewed as ensuring new AI systems are usable by and useful to people, such that AI systems successfully extend people's capabilities, i.e. intelligence augmentation. So, in conclusion, artificial general intelligence is a concept of both aspirational and practical consequences. We analyzed 9 definitions of AGI, identifying strengths and weaknesses. Based on this analysis, we introduced 6 principles for a clear, operationalizable definition of AGI, focusing on capabilities and not processes, focusing on generality and performance, focusing on cognitive and metacognitive rather than physical tasks, focusing on potential rather than deployment, focusing on ecological validity for benchmarking, and focusing on the path to artificial general intelligence rather than a single endpoint. With these principles in mind, we introduced our levels of AGI ontology, which offers a more nuanced way to define progress towards AGI by considering generality, either narrow or general, in tandem with 5 levels of performance: emerging, competent, expert, virtuoso, and superhuman. We reflected on how current AI systems and AGI definitions fit into this framing. Further, we discussed the implications of our principles for developing a living, ecologically valid AGI benchmark, and argued that such an endeavor, while sure to be challenging, is vital to exchange with. Finally, we considered how our principles and ontology can reshape discussions around the risks associated with artificial general intelligence. Notably, we observed that AGI is not necessarily synonymous with autonomy. We introduced the levels of autonomy that are unlocked but not determined by progression through the levels of artificial general intelligence. We illustrated how considering AGI level jointly with autonomy level can provide more nuanced insights into risks associated with AI systems, underscoring the importance of investing in human-AI interaction research in tandem with model improvements. We hope that our framework will prove adaptable and scalable. For instance, how we define and measure progress towards the AGI might change with technical advances such as improvements in interpretability that provide insight into our model's inner workings. Additionally, parts of our ontology such as human-AI interaction paradigms and associated risks might evolve as society itself adapts to advances in AI. Impact statement. This position paper introduces a novel ontology that supports discussing progress toward AGI in a nuanced manner with the aim of supporting clear communication among researchers, practitioners, and policymakers about systems, capabilities, and associated risks. Alright, so that is the end of that one. There's additional 5 pages of references that I'll spare you, but thanks for hanging out with me for 45 minutes while I read this, and learning a little bit more about maybe how we can codify things and describe things better and get a shared understanding of what's coming out of this giant faucet of development these days.